Welcome to Heavy Networking from the Packet Pushers Network, a fine podcast for your professional career development. I'm Ethan Banks with Drew Conry Murray, and our guest is Alex Saroyan, CEO and co founder of Netris, our sponsor today. Netris is tackling the issue of automating multi tenancy in an AI data center. You want to rent out those GPUs to various companies that need them, but you can't imagine manually standing up and tearing down VLANs and VRFs constantly, right? Yeah, I can't either. Well, Netris has your answer, and it's a solution certified to work with NVIDIA. We're going to get into the nuts and bolts of Netris network automation with Alex, and along the way, we're going to discuss not just the multi-tenancy challenge, but networking challenges common to all AI data centers, whether they're meant for multi-tenant use or not. Listening to this episode, it's going to make you smarter about AI workloads. So stick around, even if you don't think you're going to ever have that multi-tenancy problem. You're going to learn about things that you didn't even know were things, and be ready when your boss's boss's boss decides they're going to stand up that AI data center after all. All right, Alex, welcome to the show. Nice to have you today. And when we say an AI data center, would you describe that? What is it that's unique about what's happening in this computing environment?
Yeah, I know. Somehow in AI data centers, a lot of things are different, and these AI chips they are hungry for all kinds of performance. So power is different, cooling is different, networking is different, compute is different. Everything needed to be reinvented, and is getting very interesting as we're getting to the point where a lot of organizations are deploying these GPUs in their data centers.
So my understanding is one of the issues is you've spent a lot of money on these GPUs. They're expensive to run and power, so you don't want them sitting idle. But the way that the parallel processing happens, if traffic isn't making it to its target on time, GPUs could be sitting idle. Yes.
Yeah, absolutely. Very expensive. You never want them idle. Your customers who are renting them from you, they also want to get these GPUs allocated fast. They want to start using these expensive GPUs, and you want to push these GPUs out as fast as possible.
When you're doing an AI computing problem, the way it's been explained to us is there's a ton of math going on. The GPUs are in a clustered scenario, and they each get a piece of the math problem. That is, the math problem is distributed amongst the GPUs in a cluster. And if one GPU is idle because it didn't receive the next bit of information it needs to continue doing math, everybody in the cluster is sitting idle. Is that a fair description of a problem that you can deal with?
That's correct. Every GPU has a built-in memory, and this GPU can only operate with the data sitting in its own memory. Now, when you're dealing with a larger set of data, you probably need more GPUs, both from compute perspective, you want to do parallel computing, but you also want these GPUs to connect their memories into a kind of larger singular memory block, and that is a networking problem. So use networking for that, so to expand kind of memories.
We're still talking about switches. We're still talking about Ethernet and so on. So it's trying to take these networking constructs we've used in a typical data center, but sort of munging it to fit this unique use case.
Yeah, almost with some details, just to be
Please do.
technically
Yes.
accurate. Within the server, you typically have multiple GPUs, commonly 8, and within the server itself, you have technology that is connecting GPUs together. In addition to your PCI Express bus, another one, because we always thought that PCI Express is the fastest communication bus, but it's not fast enough for GPUs. So in case of NVIDIA servers, there's technology called NVLink, which is for sort of scale up for vertical scalability. So multiple GPUs can talk to each other at very high speed within
Hmm.
the single server. Uh, in newer generations, also within the rack. But that's not enough. You want to talk beyond servers, beyond racks. This is when networking comes in. And then there are different options. There's InfiniBand, Ethernet, different options to network these GPU servers together.
So the network topology for a typical AI data center leaves fine, or is it actually something else?
There's actually multiple switch fabrics. There's typically two, can be more, but two fabrics is very common example. So there's one which is kind of front end or north south. It's called this. It's more for like that one is like leaf spine fabric. That is primarily for like accessing these GPU servers, or these GPU servers accessing storage, basically for like regular networking. But in addition to that, there's also this backend switch fabric, backend, or also called east-west switch fabric, which is for GPUs talking to GPUs. And these are slightly different. There's different architectures, commonly referred as rail optimized topologies, which can be InfiniBand or Ethernet.
Okay, so front end. So I'm going to have servers that are in this architecture that are plumbed both to this front end network and this back end network. The front end network is you mentioned storage databases, that kind of thing. So it's where I'm pulling data from to feed into the back end network.
That also how you connect to these GPU servers, to administer them, to run jobs, to basically you can think like regular production.
Yeah, it's hit me that this feels like a typical data center network. Yeah, more what people are used to.
Correct. That part, the front end network is typical. It looks like kind of typical leaf spine network for production use. But the backend is different beast. Backend is for connecting GPUs to GPUs. And on a server, you typically have two NICs connected to that front end fabric or that production. Let's say you have 8 GPUs, you would have 8 NICs, which are like each NIC is aligned with each GPU. And that way you sort of have dedicated network card for every GPU. And each card is typically pushing 400 gigabits per second. So every GPU can talk to any other GPU on the network. We're talking like many thousands of GPUs. At 400 gigabits per second line rate, all at the same time.
I've seen some backend fabric topologies where it's a one-to-one, no oversubscription, but it does look like leaf spine as far as that goes. Is it? But you said it's something subtly different anyway. It's rail optimized. Can you give us a clue as to what that means?
So yeah, it may remind leaf spine fabric, but with like a lot of spines. If it's 2-tier, you would see basically whatever number of leaves you have, you would see like half number of spines. If it's 3-tier, you would see like a lot of leaves, that many spines, and half of that super spines. A lot of switches. Now, why is that? Is because when we design these networks, we need to keep in mind that these GPUs typically, all GPUs in the same cluster, if they are working on a job, every GPU will be continuously reading and writing at 400 gigabits per second, because this traffic is basically memory replication. So that's why it's continuous kind of, if you look traffic statistics, you'll see like a straight line, ideally at 400 gigabits per second. Now there's a detail. If one GPU, for whatever reason, has a limited access to network, let's say for whatever reason, one GPU is only able to push 200 gigabits per second, but others are okay. What's going to happen is, because the way these parallel computational algorithms work, they will adjust to the slowest performing GPU. So your entire cluster may end up performing at half performance. And now you're losing money.
Wow. And is that a GPU issue as opposed to the network issue then? Because it sounds like the network itself is stepping down to limit itself to what the GPU can do.
Well, if that limitation is coming from network, then it's networking issue. So basically, network engineering supports the applications, right? We as plumbers, we need to understand what these applications expect from us, what they want us to deliver, so they can perform at their full capacity, and we deliver this. It's like kind of our job to do this as plumbers, as network engineers.
You mentioned InfiniBand, and I understand that is a fabric that's sometimes chosen for AI workloads. What's interesting about InfiniBand, particularly for the backend network?
So see, because this is a memory replication problem, the whole thing, the whole story with this backend network came from solving memory replication problem. And InfiniBand isn't a new technology, and replicating InfiniBand has been used for forever for RDMA, for commonly
Right.
for storage problem. But what happened? Industry picked that same technology, RDMA, and started using it for memory application. See the HCA card. HCA is like NIC
Mhm.
in InfiniBand world. HCA card would have something like what NVIDIA calls this GPU direct, like direct memory access into GPU. So basically, network port can almost directly talk to like memory. But you need a network that is lossless because your application is basically using memory. You never expect memory to lose
Uh,
data. So your network has to be lossless. And RDMA with InfiniBand was, a network that was always designed to perform in a
right.
lossless fashion.
That is, InfiniBand, as is inherent in its nature, can deliver a lossless fabric, whereas
Hmm.
Ethernet was never designed with losslessness. We have to do a bunch of engineering around the default Ethernet behaviors to make it so that it can deliver losslessness.
Yeah, exactly. Ethernet was always like, okay, packets can get lost. Other layers, other protocols need to take care of this. That's why we have TCP. That's why we have some, even on application layers, sometimes we take care of, losing data, reconnecting, making sure that the data is accurate, because web applications, especially, they always assume that, okay, data can be lost. So I should handle this situation in my application, which is not the case for GPU, that backend communication.
Because again, the expectation is this is a memory operation. Those don't get lost. They're not going over a fabric where you're going to run into contention or congestion, and frames are going to fall off the Ethernet wire.
Yeah, exactly. When you allocate a variable in memory, you assume that variable is there. Like you never, like, you don't keep like CRC checks or something for that, right? You kind of trust that memory actually works. So now when you span that memory across lots of servers, across like 10, 20, 40, 50,000 of network ports, transceivers, and cables, you still have the same expectation. That's why InfiniBand was kind of natural choice there. But over time, actually, a number of improvements happened to Ethernet, and today we are seeing InfiniBand and some optimized Ethernet options performing on par, and we see both in
So,
production.
like QoS kind of mechanisms, priority flow control, explicit congestion notification, these sorts of implementations help make an Ethernet fabric lossless. And you want it, you want that. I mean, because you could ask the guys, well, why didn't everybody just use InfiniBand? Well, because it's expensive and there aren't that many engineers that can support it, is my understanding. Ethernet, everybody can run an Ethernet network. And in this case, it's just a matter of engineering knowledge to optimize Ethernet, as you put it. Oh, plus there's the work of the Ultra Ethernet Consortium that's going to have an impact here too.
Yeah, I think there are a few kind of pros and cons here. So I think from price perspective, this InfiniBand switches are became, I think, less pricey, and this optimized Ethernet switches, they became more pricey, and now they're getting closer. And also the GPUs are so expensive that the cost of network is just
Mhm.
smaller part of it. But I think the bigger reasons, industry, there's a lot of organizations who were willing to have Ethernet on the back end. I think that's coming for several reasons. One reason is some organizations, they are just very familiar. Ethernet is familiar.
Yeah.
They want to deal with that, not InfiniBand, which is less familiar. Uh, InfiniBand has a certain limitation, so you cannot go beyond certain scale. I think currently it is like 64,000 GPUs, if I'm not mistaken. Maybe one day it's changed, but there are also scale limitations. So like, for example, X deployed 100,000 GPUs, and that's more than what's possible with InfiniBand. So X is running on Ethernet. And to your point, Ethan, QoS and some of the mechanisms that were there in Ethernet that is used, but on top of that, industry created some additional improvements. One is adaptive routing, which is implemented through some functionality in the switches, plus some functionality in the network cards itself. So for example, when NVIDIA says Spectrum X, that's architecture, that is their Ethernet-based architecture for backend east-west fabrics. When they say Spectrum X, they don't mean just switches. They mean switches plus network cards together, because that lossless functionality is achieved through the combination of appropriate NIC cards and appropriate switches working together in concert.
Now, okay, so we got a lot of big flows going in between each of these GPU network interfaces. These are going to be elephant flows from what you're describing, right? And you're not, people can't see it, but you're nodding at me, Alex. So, okay. How does ECMP deal with this problem, or do we have to deal with this problem somehow?
Oh yes, absolutely. It's a big part of the problem. So Ethernet, ECMP, and every load balancing mechanism for Ethernet and web scale world was designed with the idea that there's large number of smaller flows, basically high entropy. A lot of basically source IP, destination IP, and protocols and ports are all very random, high entropy traffic. And this is how hardware was always optimized for. Now with AI and GPU memory replication traffic, we're seeing kind of the opposite. We're seeing what we call elephant flows, basically low entropy and lot of data. Now, ECMP is not great with that. And
specifically that one elephant flow, because there's nothing changing about the values that the switch would hash on. There's not much entropy, not much is changing, or nothing's changing. That elephant flow is going to get stuck to one member of the ECMP link bundle, as opposed to traffic being distributed more evenly through the bundle. So now we've got potentially underutilized links.
And remember, our requirement is to guarantee 400 gigabits per second full duplex between every endpoint on the network. And we're talking, many tens of thousands of endpoints.
And so what happens when two elephant flows get hashed to the same ECMP link member?
You have at least one GPU operating at lower performance. It is limited. It cannot do 400 gigs per second. It is forced to operate at lower performance, which will cause the entire thing operate at a lower performance. And you are losing money because these GPUs are now idling. They are very expensive.
So are there techniques besides ECMP that are being used then for these very specific use cases?
There's a technique called adaptive routing. This is NVIDIA specific technique, which is a functionality that you enable on the switches. You also enable on the NICs. So NICs are sending packets in a certain way to the switches, and switches load balance packets in a certain way, basically not in an ECMP way, but in a special way. You basically get optimal utilization of all links.
I thought where you were headed was adaptive routing was just a fancy way to say per packet load balancing, but it doesn't sound like that's the case. It sounds like it's subtly different from per packet load balancing across the ECMP bundle.
It's kind of close to per packet, but it is optimized because per packet is something that you don't have control from the host perspective, right? But when it is also when you can also control how your NIC sends packets and how other NIC receives packets, you can apply all kinds of optimizations there. Now this optimizations sometimes change. There's hardware vendors make some tweaks with different versions of their architecture. Uh, you know, from operational perspective, our job is to properly to configure these parameters properly, so the whole system will perform the way the vendor is designed it. But essentially, it's like, kind of smart, optimized, advanced per packet load balancing. In a simple terms, we can think that
Are
way.
there other Ethernet vendors who are also able to support AI workloads? Because we've just been talking about NVIDIA, but I know Broadcom has been trying to do some work on its ASIC platforms to help it to make them suitable for these kinds of use cases.
Yeah, absolutely. Broadcom ASIC also has functionality they call DLB, dynamic load balancing, which is again similar approach. Their approach is more, in my opinion, is closer to per packet
Mhm.
load balancing. The chip is optimized for handling that kind of traffic, and
Mm.
Arista has switches with that support this. Dell has switches with the support. Edgecore has there's more switches, and it's public information that there are some organizations very successfully running AI workloads using Broadcom based switches.
Okay. Yeah, because I guess that's part of the one of the impetuses for going with Ethernet is that there's a broader provider ecosystem than InfiniBand, which is at this point just NVIDIA.
Yeah, exactly. So I guess InfiniBand was the first technology to deliver on the requirements because it was initially designed for lossless networking, and then over some time, with a little bit delay, Ethernet, caught up, and now Ethernet is very commonly used. E- even many NVIDIA customers who are investing in NVIDIA switches no matter what. There's even if there's no like cost difference for them, many of them are opting for Ethernet, given that, if performance wise it's the same, why would I go with InfiniBand given that I'm very familiar with
Right.
Ethernet? So this is kind of common way of thinking for users.
So building these networks sounds very complicated. They're very finicky. And we're here to talk about adding another wrinkle to that, which is making a multi-tenant network to support different GPU workloads. So just before we dive into that, can you talk about what some of the problems are that come up when you're trying to build a multi-tenant environment for AI workloads?
Yeah, that's a great question. So remember, first generations of these AI infrastructures were kind of fundamentally single tenant. Even
Hmm.
if we think, for example, ChatGPT, the cluster that they are using, only them are using it, right? The idea was, let's put a lot of GPUs together, let's train these models, and then let's do inference. But it's still one entity, one organization using it. Now, over time, it started to change. Many organizations, investing in GPUs, they were started thinking, okay, how do we make this multi-tenant? And you may think cloud providers, which is the obvious case where cloud provider is, hosting GPUs, and their business is to rent out groups of GPUs to their customers, to their
Hmm.
tenants. This is one very common use case. But even beyond cloud providers, enterprises are. It is desirable for many enterprises to design their infrastructure with multi-tenancy in place. Why? Because it is very common in AI GPU use cases that someone is using very sensitive data. And
Hmm.
even if you're an enterprise, sometimes you want to share this infrastructure with different organizations within your company, maybe with your partners. And if you're a cloud provider, your business, your bread and butter is to share this infrastructure with your customers. Now, whoever is using that groups of GPUs, they are commonly dealing with such a sensitive data that it is absolutely critical for them to know that there is very high security
Hmm.
standards implemented in terms of multi-tenancy. So this is becoming very similar to what cloud providers do. See, when you're using AWS, for example, when you have your VPCs in AWS, your virtual private clouds in AWS, as a user, you never think that another VPC can have access to your VPC. It's like almost unimaginable, right? And now what if now you are in the shoes of AWS? How do you provide that kind of programmatic isolation for your customers? Your customers have seen AWS. The security in AWS is exactly what your customers are expecting. This is now the norm. Uh, so it's a major challenge because see,
Well, okay. You just made an important point here. I'm not building a network. I'm building I'm building a cloud. Is what I'm building. That is what that data center at the end is going to be. The experience that is expected and to be delivered. And so, if I haven't been doing that before, all of a sudden, it's the network that we're focused on today. But I mean, it's up and down the stack. You need to deliver. You need to deliver multi-tenancy everywhere and have it be programmatically accessible and all those cloud-like functions that we're standing up now that maybe wouldn't have been on our radar before.
Exactly. Now everything needs to be multi-tenant. Your Qt platform becomes multi-tenant, your storage becomes multi-tenant, and your networking is in the center of all these other components, right?
Mhm.
As a network engineer, network operator, you're core of the multi-tenancy. You make multi-tenancy possible in your data center. And deep inside, like if you go into the switch and like run the switch configuration, the primitives are all the same. You'll see VXLANs or VLANs sometimes, you will see VRFs. But the challenge is how to configure these VLANs, VRFs, VXLANs dynamically, automatically across large number of switches. And remember, when you are provisioning a new tenant, you have 25 other tenants using that infrastructure.
Yep.
Provisioning new tenant, you cannot turn off network of that other tenants. They are using it.
Yes, so this needs to be, programmatic. You need to be able to
Yeah,
spin up a virtual environment and be assured that you've got that virtual separation from other tenants. Probably you have some kind of SLA type performance guarantees you're trying to deliver, all on shared infrastructure.
exactly. It's not enterprise network anymore. You can't provision new tenant on the day of maintenance. It's not like that. They
Yeah.
want it now. They don't want it
Right.
after 2 weeks.
We've got a window in a month that will get to you.
Yeah.
Well, Alex, let's get into Netris itself then. And let's start. We've talked a lot about the back end infrastructure, what the data center looks like, what the network looks like, and a lot of the challenges. So Netris comes in solving this multi-tenancy challenge. How does it do that at a real high level, like your elevator pitch? Explain like I'm five, Alex.
The whole purpose of Netris, why we started Netris years ago, it was because we were seeing how 8, 10 years ago cloud was new, and we were seeing how cloud providers are automating their networks in a very different way. And we were seeing, okay, these guys are solving a really challenging problem in networking. So this is where idea came for Netris, and it was Netris is cloud service provider networking automation, but for everyone. These cloud providers created their proprietary technology. We created pretty much the same, but for everyone else. We're not a cloud provider. We help others. We help network engineers, network operators to become cloud providers.
So I'm not coming to Netris with some data I want to put into an AI to try to train a model. I'm utilizing Netris to build out my infrastructure that I can then have be a multi-tenant environment, or that I can go to a provider who's using Netris on the inside for multi-tenancy.
Yeah, absolutely. Our customers are cloud operators, and we've been working on this for about 8 years. And 8 years ago, AI wasn't as popular. But see, before AI became popular, most of our customers were tier 2, tier 3 cloud providers, like your CPU cloud providers, if you will. But from network automation perspective, it's very similar problem. In AI, you have way more switches, more networking, and that's why the pain is bigger. That's why and AI is very popular these days. A lot of organizations are building. Yes, today maybe 9 out of 10 customers is AI, and 1 is regular CPU cloud. But it's the same thing: cloud provider networking for cloud providers and for AI cloud providers.
Well, because now anyone that's buying a bunch of GPUs are trying to get their money back out of it, so they'd like to be a cloud provider if they weren't before.
Yeah,
It's an economics thing.
and even enterprises. We work with financial organizations. We work with universities they are obviously not cloud providers, but even they want to build their infrastructure fundamentally in a multi-tenant way. They want to have that multi-tenancy feature designed in their infrastructure. So one day they need to share even with internal tenants. They have at least a possibility of doing it.
So if I'm a jaded network engineer listening to this, I'm thinking, so Netris is just kind of offering me some fancy VLANs. Is there more to it than that?
So I like to explain this through 3 pillars that we enable you with. So pillar number 1 is what we call the notion of VPC. VPC as virtual private cloud, like the VPC in AWS. Now, typically in networking, everything is tied to switch boards, right? Not to end servers. Now, with the notion of VPC, you can tell your networking controller to create isolations, create networking constructs by not only by referencing switch ports, but also referencing servers, referencing VMs. And server is a very important building block in AI cloud. Now, it's notion of VPC where you can say, hey, this is tenant 1. My tenant 1 should have access to server 5, server 22, server 29, enter, whatever. Now, the software that's running underneath, Netris software, it knows your topology, it knows your network configuration, it generates your network configuration. So basically, you provide that simple input, and our algorithms automatically translate that input into actual configurations. Just an example, NVIDIA's configuration guide for this Ethernet backend network is 130 something pages long document, which is basically telling you how exactly you're supposed to configure this VXLANs, VRFs in a certain way. Our software knows that certain way. And instead of you figuring out how to do all that and then figuring out how to automate that, you get that automated from day 1. So we raise level of abstraction for you. Now your network becomes very abstract. We give you this cloud provider abstractions. So VPC is the minimum. VPC is this one fundamental building block. And then there is this question of, okay, VPC helps me isolate groups of GPUs, groups of servers. Okay, there's more. How do I make this VPC talk to that VPC if I need that? How do I make my isolated VPCs talk to shared storage VPC? Because even though there is multi-tenant storage, but it's still on networking guys to enable the traffic to go from this isolated VPC into that amazing multi-tenant storage system, right? So this is second pillar, which we like to call cloud networking constructs, cloud networking functions, where you can do things like VPC peering, things like internet gateways when you want to enable internet for the VPC, things like NAT gateways, things like elastic load balancers.
It's all sounding very familiar, Alex. Yes.
So with first and second pillars, we provide you this cloud networking constructs, which are kind of business values, right? These are constructs that help our customers become cloud providers, simplify consumption of these cloud constructs. And there's this third pillar, which is the operational aspect of it, because don't forget, all this amazingly programmatic network still needs maintenance, and it's still network engineers who are responsible for this network. Is their job, and these are very large networks. How do I design these networks? How do I uh, put together my source of truth? How do I install switches, upgrade, downgrade switches, monitor these switches? So we have this third pillar, which is the fabric management, the operational aspect of that, which basically helps network engineers do their everyday job. And all these processes are streamlined and optimized for cloud provider use case. You can say things like, hey, I am deploying NVIDIA Spectrum-X based AI architecture. Netris knows what that is. Netris would tell you, hey, how many servers do you have? What is your scale? And then Netris will help you to generate your source of truth, to onboard switches, to install, automate switches, and you can go live in like few hours, like instead of like months typically.
Well, you said fabric manager. Is that like a controller?
Yes.
Okay. So I'm as a network engineer, I'm interacting with a controller. I'm using the controller to establish what I want the fabric to look like. You talk to the switches that are out there. The controller talks to the switches that are out there, and then can you can push whatever config is needed. You're not pushing. You're not talking to the forwarding table. You're talking about configuration and standing them up via configuration standards so that they behave the way you want them to behave. How are we talking? How are we actually talking to the switches? Is this like netconf? What are we doing?
On switches, we have a lightweight agent developed in Go. It is using very little CPU resources because it's written in Go. It is communicating with controller using your out-of-bound management. It talks to controller. Controller knows what you want to achieve. Like maybe controller knows your topology, and the agent has logic, which is like, okay, my switch is connected to that switch with this switch ports. Okay, I know that I'm running in this kind of operating system of this version, and best practice for switch to switch communication in this environment, in this use case, is to use BGP, EVPN underlay fabrics using this kind of templates. This is tested, this is best practice, and agent will implement that. So that way, agent goes in a closed loop in every minute. Whatever changes you make in controller, they apply in a minute automatically throughout the fabric. Not only they apply, but also everything we configure, we set to monitoring. So we bring switch to switch links up with BGP. We would monitor that. If something goes wrong, we will inform. Just like that, the entire monitoring is automated. There's no need to set up any thresholds or something.
Agent running on the switch, that lightweight agent, is a bit of magic. It's hitting me like, okay, the controller can talk to the agent. That can be unified, whatever the command set is that you're setting there. The agent is the abstraction layer for whatever switch that it's sitting on to translate the configuration instructions it's receiving from the controller into configuration standards that the switch requires. So you write an agent per switch platform that you support then?
That's correct. It's different for every platform. It has the best practices are different. How you configure things to work the best in NVIDIA versus Arista, for example, two very different things, different commands, even different approaches sometimes.
So what switches are supported then?
So currently we support all NVIDIA switches through Cumulus Linux. We support Arista switches through EOS. We support Dell and Edge Core. These two are through Sonic.
Sorry, I just want to clarify. You said the NVIDIA switch is using Cumulus Linux, so that's not the Mellanox NOS?
Long time ago, there was, I think Mellanox had Onyx operating system, but after NVIDIA acquired Mellanox and Cumulus, Cumulus became like the main, the most recommended kind of operating system of NVIDIA.
Okay, got it.
Even the command line is now called NVIDIA Unified Experience CLI, something like that on Cumulus.
Okay, okay.
Branding, yes. So another piece of this that I'm curious about, smart NICs or DPUs, is there a role in that in the Netris world for those?
Yeah, absolutely. So for east-west fabrics, the NICs work in smart NIC mode. Smart NIC mode means that NIC inside has something smart. It does some advanced things in terms of packet forwarding, and that is very important for adaptive routing. Now that thing needs to be configured from the host system, and you have 8 of those. You're also supposed to configure, IPs and routing from the host perspective in a certain way to make all this real optimized story work right. Now we have a plugin that goes into host, and that plugin communicates with the switch using some custom LLDP protocol that we've designed. It's super safe, and because it works on tenant's host, right? It cannot contain information about Netris controller, any authentication, because that could be a security risk. Anyways, this thing configures the host networking and configures SmartNICs in a certain way to make the east-west fabric work. Now, in addition to that, there's also DPU situation, which is different from SmartNIC. The story with DPU is different because DPU is more like a switch between your switch and the host. DPU itself has its own forwarding, routing cables, and you have to literally configure these things. Otherwise, like traffic coming into like outside port will not end up in the system. This DPU part is solving a granular multi-tenancy problem, which is kind of a little bit future thing. We're currently working on this. There's only one hyperscaler that I know of using DPUs in this way because it's very kind of new approach. We're actively working on extending our notion of VPC, multi-tenancy, and these cloud constructs into the DPU. So you can think about it as if having another switch, but it is inside the server. And you can directly connect a VM or container or namespace to that switch. And you can apply networking, ACLs, you can make it part of VPCs or, any kinds of networking rules, but on that very granular kind of VM level.
So do you support some DPUs and SmartNICs today, or is that like something that's interesting to do in the future?
So we support NVIDIA BlueField-3 SmartNICs today. This is in production. Customers are using. It's like a requirement of that Spectrum-X architecture. We are working on supporting BlueField-3 DPUs. That's a work in progress, and that part we're planning to make it, beta version in 2 months and production version around August.
Can you talk a little bit about the controller platform?
Yeah, so Netris controller runs typically on 3 servers for high availability. You can run on 1, but recommended to run on 3 for high availability.
If you're already spending the money on the GPUs, you might as well. Yeah.
Exactly.
Splash out for a load balanced solution.
From technical perspective, if controller is not available, your network will continue operating, but you cannot make any changes on the network. Anyways, controller runs on 3 servers. It can run in air-gapped situation with online installer, offline installer. Technically, it's a Kubernetes cluster. We basically turn that 3 machines into Kubernetes cluster and run containers. Our controller is containerized. It runs on Kubernetes cluster.
What kind of scale can I get out of this controller?
So we've tested this controller on a large scale. One object that you have the most is your network links. You have more links than anything else. And we've tested our controller at the scale of 50,000 links, and it is optimized to work well at that scale.
50,000
which is basically 2 times more than our largest customer.
Okay.
which is considered which is not considered a small customer in AI world.
But if I was bigger, it sounds like all I'd need to do is throw more worker nodes into the Kubernetes cluster,
Yes.
and in theory, it's that simple.
Yes, exactly. We continuously revalidate our controller for larger and larger scale. Whatever, like we have the sense of what's our customer scale. We always make sure that we are like minimum twice. We can support minimum 2 times more scale at a given time.
So 50,000 links, you said, is there a number? Do you also have like a number of what's sort of the maximum number of VPCs or virtual environments I could support?
So controller itself can support theoretically unlimited number of VPCs. Now, let's not forget that these VPCs are using VXLANs, which is you can have only 16 million of those, which is large number. Now,
Yes.
VPCs are implemented partially through switches. So VPCs are VRFs on the switches, and switches have limits of VRFs, which is okay because some switches are limited to 1,000 VRFs, but you don't need that many VPCs on one particular switch.
Mm-hmm.
Typical AI cloud providers, they are under 1,000 VRFs on entire setup. But we're talking hypothetically. Maybe you want to know that your system can do more than you need to, right? It's more scalable. Even at a larger number, it will be distributed across many switches because you can connect only so many GPUs to one switch. Because of that, the limitation of maximum numbers of VRFs per switch is not a problem. But there's one more thing. I mentioned this NAT gateway, internet gateway, elastic load balancer. So in traditional and enterprise networking, these functions are delivered through dedicated firewalls or load balancers. Now, the challenge with that is that things are designed for enterprise, not for cloud provider. How do you make reconfiguration of load balancers and firewalls in connection to your VPCs? And like your customers would request and destroy elastic load balancers every minute. How do you reconfigure that? It's a problem. Now we have a component we call Netris Softgate. Hyperscalers, similar approach to Softgate. Now Softgate is a Linux machine with lots of Netris, optimized configurations. Essentially, it's multiple machines, typically minimum 4 machines connected into your switch fabric using same EVPN, BGP, VXLAN method. It's not using VLANs. It's not limited to VLANs. So it's based on VXLANs. You still have these 16 million units of those.
Mm-hmm.
Now, Softgate is designed with horizontal scalability. It is designed for cloud providers. It understands VPCs. It is configured automatically when you call Netris API saying, hey, create an elastic load balancer or create a NAT rule. Softgate nodes automatically configure. But here's like, how do I scale these nodes? Because it's software performing networking functions, right? Now, we designed Softgate in a way that you can always add more Softgates in the cluster, and your traffic will automatically rebalance between these nodes. We have many algorithms there. There's like, I can talk for hours about how it works underneath, but long story short, designed for scalability. But you need to keep adding hardware, of course.
Mm-hmm.
Yeah, well, it reminds me of the architecture service providers who need to do a variety of virtual network functions for whatever their reasons are, and they can just, the way they built out the clustering, they can throw commercial off the shelf at the clusters and keep amping up as they need. Okay, Alex, so another important piece of this here, integrations, in that if you're building a cloud now of which networking is just one problem to solve, does Netris integrate with other software that I might be using in my AI data center?
Yeah, see, not only networking has to be multi-tenant, but these other pieces of your cloud should be multi-tenant, including your compute, your storage, basically everything. Now, of course, Netris can solve all problems. Netris only focusing on networking. There are other companies that are doing really great job on their piece. So, and we are open. We work with many companies on the ecosystem. Particularly, we recently announced our collaboration with a company called Rafe. Now, Rafe is compute automation platform that is enabling companies to launch self-serviced uh, platform as a service offerings. They basically they manage compute, they manage Kubernetes cluster, and they provide this customer-facing user interface. But they need networking to create all these VPCs and manage switches. Now there's a integration on API levels of two products, which together these two products provide that kind of end-to-end experience for cloud providers.
So with the API, then maybe I'm not using Rafe, but since it's an API and maybe I've built my own platform of some kind, I can integrate Netris with the API then.
Yeah, absolutely. Some customers they build their end user facing portals themselves, and for them, Netris API becomes their backend for all networking functions. Something else becomes.
Now we're really abstract.
Yeah.
We got we got the abstracting controller behind the abstracting agent, and now we've got an API behind that if we want. So yeah, okay. It's amazing any of it works, and it's awesome that it all does.
Yeah, the cloud architecture is that networking has its own controller, storage has its controller, compute has its controller, and there is kind of a console, like controller of controllers, if you will, a console that is customer facing, but on the backend it is talking to different controllers, not to devices, because one tool cannot orchestrate everything in the cloud. It's too much for a single tool.
Mhm.
Now, speaking of tools, you guys have built a tool along the way called a Cloud Sim that is helping. Well, you tell us, Alex.
Yeah, so when we were working with NVIDIA, we learned from NVIDIA how to use their platform called NVIDIA Air, which is great idea, infrastructure simulation, digital twin for infrastructure. And we were using that for different use cases. And we also have our physical lab here in Santa Clara. Some things have to be tested in a physical lab. But see, not everything can be tested in physical lab, and not everything can be tested in NVIDIA simulation, because that is for NVIDIA. For partners like us, it is somewhat limited. Eventually, we had this challenge of how do we test and validate our technology's limits at a insanely large scale, like 60,000 GPUs, 100,000 GPUs. How do we simulate that kind of large network? So we ended up creating a tool for that. We call it Cloud Sim, which is essentially infrastructure simulation platform. You create digital twin of your infrastructure. It is integrated with our controller. NVIDIA Air also is integrated with our controller. You can do both. But Cloud Sim is more optimized for our use case, and it is optimized for scale, for testing at scale. There's no limits for the scale. You basically, you want a bigger scale, you add more hypervisors, and you have bigger scale. And to simulate, just to give you a sense of it, to simulate 8,000 GPUs, we only need 4 hypervisor servers. And 4 hypervisor servers can handle networking, simulation of networking, not performance, just simulation. Now that became amazing tool for our developers, but we started using this with partners, with customers, and today Cloud Sim is basically where every customer would do, evaluation of Netris, training for Netris. Even when they deploy their production, they are waiting for switches to arrive, and they are waiting for switches to be racked and stacked and mounted and cabled. While they are waiting, they start building their infrastructure in the simulation. They finish software part, hardware part is ready, and then they just move Netris controller configuration from simulation into production. It makes life so easy.
So I'm almost pre-staging my configuration in Cloud Sim, and it's ready for me when the hardware's there.
Yeah.
So if I'm, going to build out a service renting GPUs, or I need to do it internally, Where does Netris sort of fit into my buying cycle? Is it part of my bill of materials for the data center? Do you come in earlier, later, or what's ideal for you to come into the buying cycle?
It is ideal for us and for the user if we come early on. So before your hardware is delivered, the best time for Netris to get in is day zero, before even you power on your hardware. And for this, we can partner with we work with system integrators like WWT or like others, like typical system integrators.
Hmm.
We can also work with NVIDIA. We can partner with their implementation services too, but we also do directly. All permutations of setup are okay, but it's the best that Netris comes in on day zero. Now, with some customers, they deployed something and they tried to either do this manually or build automation in house. And eventually they decided to switch to Netris. So they came in to us when their infrastructure was already running, brownfield situation.
Hmm.
That is okay. We can deal with that. The only difference is that brownfield is just harder. It takes more effort from one of our professional services architects,
Right.
and also it takes efforts for the customers.
Okay, so sooner is better.
Exactly.
Okay, Alex. So we've had a great discussion about the challenges of AI data centers and what you guys are doing at Netris, delivering multi-tenancy in an automated way. And it's funny, we scratch the surface like, oh, it's, you do some config. And then it's like, oh, no, there's also this. Oh, no, we also handle this. Oh, we can integrate here as well. So there was a lot. This was nice. The deeper we went, the deeper it got. So that was a great conversation. If people want to find out more, this was maybe the starting point of their research on this problem, but they're ready to find out more about Netris. Where would you send them?
To our website, netris.io. And if you're building an AI cloud, or if you're building multi-tenant network or network that needs automation or multi-tenancy, I just recommend scheduling a demo meeting with us. It's free. Let's just get on a call. Let's get to know each other and see whether Netris can help you. If yes, good. If no, fine. We'll be just happy to talk engineering. Always fun.
I'm looking at our notes here, and it says netris.io/demo, and someone can pop in there and schedule that demo with you guys if they want to see more detail what's going on.
Correct.
Okay, sounds good. Thanks, Alex. And if people maybe they want to hit you up with some questions, where's the best place to find you? Are you LinkedIn, maybe?
Yeah, LinkedIn or X.
LinkedIn. Oh, a holdout. He's still on X. Oh, look at that. All right. Okay. Thanks again, Alex, for joining us today, and to Netris for sponsoring. And thanks to you out there for listening to Heavy Network. We hope that you learned something about the peculiar problems of data centers that are designed for AI compute. And I don't know, you think networks are more or less the same, right? I just used to feel that way. And then you get into these workloads that need this. The network's got to behave this certain way, and then the details get complicated. Whatever. Complexity. It's inherently challenging to scale, and that is where software solutions can abstract that complexity and keep track of the details. Humans become the difference between success and failure. So if you chat with Alex and the team at Netris about their multi-tenant AI data center solution, please let them know that you heard about them on Packet Pushers. That would help us very much, because that lets the sponsors know that, hey, you're listening and you're interested in what you're hearing, and it helps keep the lights on around here. Until next week, do all the things: like, subscribe, share, comment on your podcast listening client of choice, including Spotify, Apple Podcasts, and YouTube. And last but not least, just remember, too much networking would never be enough.